milli, micro, nano, pico. -3, -6, -9, -12. Okay, so we have 81.6 picoseconds. How long is this going to take to fully charge? 408 picoseconds, because it takes 5 tau to fully charge. Nano, not pico. Do what? Yeah, multiply it by 5. So fully charged is 5 tau. Okay, so we take our 81 nano, we multiply it by 5. So it's going to be fully charged at 408 nanoseconds. So with that, we can already identify, before we even get into any of these calculations, we can already identify one of these ones that we're looking for the times. And which one and why? 350.88, 100 nano, and 1.5 micro. It's going to be fully charged because we've hit our 408 nano. So we know at this point, anything after this point, our capacitor is fully charged. So with that, what is the voltage of the capacitor at 1.5 microseconds? 14 volts. What's the voltage of the resistor at that time? 0. Okay, one of the tricks we can look for right off the bat. Okay, anything else? Is 350.88, is that any one of our taus? 1, 2, 3, 4, or 5? Okay, so we're at 4.3 tau. So we know that it's going to be in between in our range. So 4 tau is 98.2, 5 tau is 99.3, so we're going to be looking somewhere in, the 99, 98.7, 98.7 range, just roughly as an idea for what our voltage should be. Because we're not quite fully up to that 5 tau mark, but we're above the 4 tau. So we should know at least the range that our answer should fall in. All right. So now that we have those, now we need to start solving for these individual values. With DC, it is nice because these guys just add and subtract and take away from each other. When we go to AC, that's not the case. It's not easy anymore. So we need to find the voltage of this capacitor. That's the equation that we're looking for. So the instantaneous voltage, because we're basing it on a time, is equal to voltage final plus V initial minus V final times e to the negative t over tau. Okay? What in the question it says to assume our C1 has no initial charge. So that's where we're charging it from. So 0. So we need to solve for this value. So the voltage of the capacitor is equal to, what's our final voltage? 14. We're trying to get there. Plus 0 minus 14 times e to the negative t, which we have here. Divided by our tau. And at this point, we are just solving for the voltage. when you're putting these in, make sure you use lots of parentheses. So what do we get? 13.81 volts. Which again, if we take our 14 volts, we multiply it by the 98.7, we're right about there. Yep. Well, it's negative 14 times this value, and then you're having 14 added to that value. We could use one of the other specialty formulas that we have. Honestly, I like using this one because it keeps everything straight. You know, as I'm writing things down, I'm like, okay, I'm going from here, charging to here. It just, there's a few more things to enter in, but it keeps everything straight for where we're at. Okay, so we have 13.81 volts. At that time frame, what is the voltage across our resistor? Huh? 189 millivolts. Yep. Because with DC, we can do that. Because there's no phase shift, there's no changing. Because what is our frequency with DC? 0. There is no frequency. It doesn't change. Frequency is the number of oscillations per second. Okay? That's the biggest thing to remember. With DC, there should be no oscillations. What you're hearing is a 60 hertz. That's what you're hearing, that little tick every so often. If you time it, it's about a second. Because that's what you're hearing. A lot of times when we're doing stuff in lab, you're going to come across things and you're going to get a weird signal that comes in. And most of the time, if you zoom in, it's going to be 60 hertz. And so what we'll do is, and what these power supplies do, is they filter out 60 hertz. Anything that comes in at 60 hertz after you've amplified it, turned it into DC, it just filters it right out. Because if not, you get this noise, and you're going to see that on some of your circuits because they're not going to be grounded properly. They're not going to be filtered, and you'll get these really weird harmonics sometimes. So when you start working with 120 hertz, 240 hertz, anything that's divisible by 60, you're going to start seeing these 60 hertz spikes come in every so often, and it's going to completely throw off your measurements. And you're going to wonder why. That's why. Because our power is 60 hertz. Huh? Well, it's not just the universe. It's RF hates you. Radio frequencies. They like to screw with things. Like I said with these lights will absolutely screw with your readings when you get into AC. Depending on the frequencies you run, I can't remember exactly what these guys operate at, but one of the things that they put out is a waveform of a frequency. And you start approaching that thing, these things raise hell with them. So one of the things too is if you're starting to realize your readings are wrong, lean over top your board when you do your measurements. Your body will block those signals from getting into your circuit. It's weird. Like you can put your hand over it, and as you run your hand over the top of it, you'll see your signals change. And it's because of these stupid lights. It's the ballasts and the lights, yes. Or there's some feedback coming in on the radio, one or the other. Okay. So at 350 nanoseconds, this is our voltage. Now we want to solve for our next range. So at 100 nanoseconds, what are our values? Again, we're going to put into the same formula that we just used. We're charging to 14 volts. And then this time we have negative 100 nano divided by the 81.6 nano. So now, looking at our time frame, what should our voltage be around? How much is 1 tau? 81. And how much time are we looking at? 100. So we should be just slightly above our 1 tau mark, which is 63.2%. So my guess is somewhere in the realm of 70-ish, maybe 70% of our total voltage, just as a rough idea. So with that, we have 14 times 0.7. We should be around 9.8 volts, give or take a little bit. Huh? What is it? Damn. It's like I know this or something. No, this is one Carson asked about. He asked about this one, and then I've changed the value since. So, but like I said, these are what I'm trying to show you guys is not necessarily how smart I am. I'm trying to show you guys ways to, because there's professors that do that. Like that's their whole goal is to show somebody how smart they are. I don't give a crap. I really don't. But the idea is start using these things to check yourself as you're getting your answers. Does my answer make sense? Well, why? Think about where these values lie in the grand scheme of things in our equations. And, start doing some of this mental quick math to say, I'm guessing it's going to be around here. If it's not, obviously, my guess isn't great. I'm not going to lie, I kind of surprised myself when that happened. But it's just have an idea. I knew it should be around there. If I'm within a volt or two, I'm happy because it was just a very rough estimate. Okay? But use these things like what I'm talking about and use them for yourself when you're analyzing these circuits. That way you can have more confidence in yourself that you're getting the right answer. Okay? Yes, Simon. Huh? Yeah. So we'll finish up with this one here in a second. So on our original equation, at the 500 or 350 nanoseconds, this is the voltage we had. We have 14 volts to start with for the whole thing. That has to be split up between those two components. So we're dropping 13 volts across our capacitor. The rest has to drop across our resistor. And so what we're seeing is we'll have the 189 millivolts is across the resistor with 13 across the capacitor. So same with this guy. Right now we have 9.889 volts dropping across the capacitor at 100 nanoseconds. How much do we have dropping across the resistor? 4.111 volts. Because with DC, it's going to split up completely evenly, and everything is going to add together. Now, in AC, so Kirchhoff still holds true. The voltages will add, but they're not going to look like they add together because they're out of phase. So we have to convert everything down to rectangular notation and add them together, and that's when things will add up correctly. But just taking the values in AC, they won't add up. So, but they do in rectangular notation, not polar. We'll be learning that next week, or week after, sorry. The capacitor would still charge to that same value. It would do it quicker. And so what you're going to see is, because our voltage supplies, they have some internal resistance. We try to make it as small as possible, as close to zero as we can get, but there is some resistance. So what happens is the rest of the voltage that the cap doesn't see is being dropped across our supply. So, and that's why it'll change the numbers, and then it'll ramp up, and then it caps out at whatever the set point is. So internally in the power supply, there's some voltage somewhere that's being dropped. All right, and then we also found out for the other one, at 1.5 microseconds, the resistor is 0 and the capacitor is full charged. Any questions about that? Or about this concept?
I did double one from it, where the charge starts at 1 volt and then moves on 4 volts. I didn't know quite how to get the answer to that.
Okay. We can go through one of those as well.
Does that have to do with inputting the initial voltage into the equation?
Hmm.
Okay, then I got that wrong.
Nope. Natural log of values. So you're getting down because we're solving for time. Any questions though about finding voltage with the capacitor? We're still going to be using this formula. We're just now going to be solving for a different value. Okay? So the idea is, let's zoom in one more. So I got my circuit. I have 100 microfarad. I've got 1K ohms, and I've got 10 volts. We'll just keep things on tens. Okay? What is my tau? So 1/10 of a second. Fully charged is how long? So half a second. So these are going to be going really quick. What I want to know is how much time does it take for my capacitor to go from 4 volts to, actually let's change that. Now I'm thinking about this a little more. Let's go from, let's go from 2.1 volts to 3.3 volts. There's a reason I picked these values. 10 volts is the final. We're trying to charge to 10. I just want to know specifically how much time is it going to take to get from this point to this point. So think about it as our graph. I want to know from this section to this section how much time we're taking. The initial we're charging from 0. So assume our capacitor is discharged. Nope. Yes. Correct. That's the idea here, because we have the same circuit, so we're still charging. We're not stopping the charging at all. We just want to know, as this thing is charging up, trying to get to the 10 volts, how long does it take to go from this point to this point? We know how long it'll take to fully charge, and so we're just looking for the small little section when the voltage gets to this level and then when the voltage gets to this level. How long does that take? The reason that specifically these are, or why this is important, why I chose these numbers, is this is kind of no man's land for digital. Okay? Yes, we'll use the natural log for this. Yep, and then we solve for t. Okay? So the idea behind this is anything below 2.1 volts-ish is considered a low in digital. Anything above 3.3 volts is considered a high in digital. Well, if it's not a low and it's not a high, what is it? It's unknown. The device will kind of make a guess in this realm. And we don't want our digital devices to make a guess. We want it to know. So in this time frame, we want this to be as short as possible. That's why I threw these numbers up there. Because when we're charging, we do not want to hang out in this zone as much as possible. We do not know what's going to happen. It's just however it happens to pick it up. Once it gets over this 3.3, it's a 1 or a high. Once it drops below the 2.1, it's a 0 or a low. We know that for sure. This realm is what can get scary. Granted, why would we be putting into a 10 volt signal into a digital system? Yeah. But the idea is we want to watch out for this zone. So, first thing we're going to do is we set our equation up. So VC is equal to V final plus V initial minus V final times e to the negative t over tau. Okay? The values we're going to have is the voltage of our capacitor is going to be this 2.1. We'll solve for this value, find out how much time it takes as it's charging to get to 2.1. Then we're going to find how much time it takes to get to 3.3 volts. And then we're going to subtract the time from there. Because we're not interrupting our circuit, we're just going continuous. That's the big thing too, is unless the problem specifically says we're stopping this at the point and then moving forward, assume that it's all one continuous stretch. Or we've turned it on and it's been running for a while. Okay? So when we're solving this, we're going to have the voltage of our capacitor minus our V final, and that's equal to the V initial minus V final. We divide both sides. We get V the capacitor minus V final divided by V initial V final is equal to e to the negative t over tau. Now is when we apply the natural log to be able to get access to that exponent. So the natural log of capacitor voltage minus the final over V initial minus V final is equal to negative t over tau multiplied by negative tau. And so we end up with negative tau times the natural log of the VC minus VF over V initial minus VF. That gives us the time. So without putting in any of our values, we can go through and now we can use this formula to solve for the time on any of these equations. Where'd I lose you? So remember when we go from here, we can take the natural log of this to drop the exponent down. This is going to equal some number, so it's going to equal all this other stuff. We take the natural log of both sides, so it's the log of base e is equal to, or times the number equal to our exponent. Logs and natural logs is just the way that we use to remove the exponent from the number to be able to get to it so you can manipulate it.
How do you know if you use a natural log or log?
Natural log is when we have e. Log is when we have any other number. We could have the base of pi, and we would just use log. ln is just a special case for when we're dealing with Euler's constant, which is the little e. All right, so what is the time that we have at 2.1 volts? Point what? Milliseconds. Okay? And then we need to go to 3.3 volts. So use this equation again and solve for it with Vc is equal to 3.3. Because again, it's still the same circuit, it's still charging. We just want to start the timer when it hits 2.1 and stop the timer when it hits 3.3. Well, they just represent a specific voltage because, like I was saying, with digital, that's no man's land. So if we can shorten that time, that's what's going to be best.
They don't. It's just numbers we keep along the.
Just along the curve.
They're not like specific.
Nope. Yeah, the only reason I picked those was just to show the digital thing. That's it.
So that's the direct formula to find any time for energies, right?
Mm-hmm.
Okay.
Yeah.
I just did all the work and verified it. All the work is done right there.
Yeah, all the work is done. But the idea is I still want you guys to be able to go from this formula. This is the formula you need to memorize. Not these ones, not other ones that we use to maybe solve for tau, because there may or may not be questions on the test that are asking you solve for the capacitor value to achieve this much voltage in this much time with this resistor. That's what I'm saying. Memorize this formula and you can solve for any of those variables. Okay, so what's our time for the 3.3 volts? Okay, so we're looking for the difference in time between it takes to get to those 2 points. 16 milliseconds. How much? I'm just putting the delta there just to show it's the change in time that we have. Okay, how much time elapsed from this point to this point? 16.506 milliseconds. And again, like I said, in the digital world, that's important because we're going to have chips and things that have a refresh rate. And what the refresh rate does, it's how how fast they sample something. So if you have things that are moving, at gigabits a second, you figure that down in there for the time of how long it takes it to execute one cycle. If this is going faster than this value, it's going to grab values in here, which it's not going to know what to do with. So it's going to take it and it's going to make it choke and give us some random output of our circuit. So if we can get this up to where this is fast enough to where we're sampling it, maybe we'll catch one in here, but odds are we're going to catch ones on the outside and on the inside of where we want it. We want to see it low, and then it'll change so it's high. But just know that, that's kind of the scary zone. That's why we need to know how much time is there so we can build around it. Or we have it delay. We have it watch the voltage. Once the voltage comes up to 2.1, we want it to wait 16.5 milliseconds at least before it samples again, which we can do. We can program things to do that. We can program these guys to take, to get these samples anytime that we need it when we're building these things. This is getting into some technical stuff, third, fourth, fifth semester, but just so you guys know, this is why we do this. Yes.
So for the value of the voltage for the capacitor in the equation, where did you get that from?
The which one?
So in the final equation that you have to do now,
Okay.
the voltage of the capacitor, how did you find that value?
I picked them.
Okay.
That's the 2.1 and the 3.3.
Okay.
There could be times that you want to know, okay, how long does it take it to go from 0.1 volt till it gets to 7 volt? Whatever your application is, that's kind of the idea. Is we can have this range and we can decide what do we want it to wait for.
And then the voltage finally, the 3.3, or was it the 10?
It's the 10. It's the final voltage the capacitor is trying to get to. Now, if we had multiple capacitors in this circuit, that's going to change things. So what it'll change is it's going to be like, okay, now those capacitors are going to be splitting up like what we did before. So they're only going to charge up to a maximum value. This V final is the max value that capacitor can go to. Okay, questions? Does that help answer your guys' questions on that style of quiz? The whole idea is just learn how to manipulate this equation to get whatever you need out. You could even solve if you had the voltage of your capacitor, you had your final voltage, you had your time, you had your R and your C, you could find out what this thing started out as. You could find out how far this capacitor was going to charge to based on what it got to, how long it took it, and what it started out as. Mm-hmm. And that's the thing too, is you can check, what is my, biggest thing to check, what is my tau versus my time? If my time is over 5 tau, it's going to be max for either charge or discharge. That's the cool thing too, is these ratios still follow the same. A capacitor is going to discharge at the same rate that it charges. So when it discharges, it's going to drop 68.3% in the first tau. Then it'll drop down to, the different levels. So charging and discharging follow the exact same curve. Any questions? Okay. So as far as capacitors goes, that's the primary focus of what we're going to be talking about for this portion of the class for now. Once we get into AC, capacitors are going to have a lot more effect on our circuits. They're kind of cool. We can use capacitors to hide resistors. So from AC at a certain value, you could completely negate a 15,000 ohm resistor. Because essentially you put a short around it with AC. So it doesn't even see it. Because you need the resistor there for DC purposes. But for AC, like on those amplifiers, you don't want it there to AC because it's going to affect how much you can put out of your amplifier. Yep. You need it there for AC, but you need to hide it for AC. And capacitors are how we do it. They're cool. All right. The next topic we're going to go through is we're going to talk about diodes. So we're shifting things a little bit. Diodes, this is their schematic symbol. Okay? This is the cathode, and this is the anode. The cathode is negative, anode is positive. So diodes are control devices. They are used to control the flow of electrons. They're used to control the circuit. Just like capacitors, we can use them to charge, discharge, that kind of stuff. but diodes are the first set of controls that we're going to use. Think of it as a valve. It's a one-way valve. It only lets current flow one direction to a certain extent. Once you get over like your voltage, you can start forcing current going through the other direction, which is how Zener diodes work. We actually build them to control the amount that they flow backwards. So when we build these guys, we quite literally, we take the silicon and we dope one part of it positive, we dope the other part negative. So for negative, we would use boron, because we need more electrons to come into this space. So we would dope this side with boron, and we would dope this side with arsine, for example, arsenic. So what we end up with is this junction where we have a lot of positive ions and a lot of negative ions. And so when we apply a positive voltage over here, it's going to draw these negative ions across, and it's going to allow current to flow. If we put a negative charge over here, it's going to repel the negative ions and get them farther away, makes it so electricity cannot flow across that component. And with diodes, like I said, they're based out of silicon, but we have a couple of different flavors. We can make them out of silicon, or we can make them out of germanium. There's still some others, but the primary two we use is silicon or germanium diodes. And the difference is, in materials, is germanium diodes cost a little bit more, but they have a smaller voltage drop. So when they're on, they're going to require a certain amount of voltage. For silicon, it's a 0.7 volt drop. For because silicon by itself has got a pretty stable shell. But when we start doping it like this, it makes a perfect conductor. Plus, it's really easy to absorb those materials into the crystalline structure of the silicon. And so then it gets the electrical properties that we need it to have. So a silicon diode is equal to a 0.7 volt drop. A germanium diode is a 0.3 volt drop. So when it's operating correctly, it's going to drop this much voltage. When it's in backwards, it's going to act as an open. It's a gate. It's going to shut everything down, not allow any current to flow. And we treat it as if it was an open, and it's going to drop all the voltage across it. There are thresholds, there are limitations, and once we exceed those, we'll start to see it break down. And if it breaks down too much, it's going to burn up. Just like resistors, if we put too much power to them, they'll burn up. Diodes, if we put too much voltage, eventually the current's going to force its way through this device and generate more heat than what's able to hold, or what it's able to hold. When we have these in a circuit, we're going to refer to diodes as one of two things. We're going to have them referred to as either forward bias or reverse bias. So forward bias this is operational. It's allowing current to flow. Reverse bias it's acting as an open. It's stopping current from flowing in this circuit. So with this, in this circuit with a configuration like this, we would have 5 volt supply, we would have a diode, and if we don't tell you, assume it's a silicon diode. So if we don't specifically say we're using a germanium here, assume silicon. So with that, what's going to be the voltage across our resistor? What's going to be the voltage across our capacitor? Across our diode. We'd have a 0.7 volt here, because it is in forward bias. And 4.3 is dropped across the resistor. Yes. And then assume silicon if it's not specifically called out. Okay, so if we took this diode and we flipped it, what would be the voltage of the resistor? 0, because there's 0 current flow. And what about across the diode? It's going to be all 5. Remember, we treat it as an open. Yep, our meter will connect the circuit. We're going to get a very small amount of current, but it's all going to be dropped across that spot. And we will have 0 current flow. Okay? So in our first position, if we have 4.3 volts, let's say we have a 1K ohm resistor, how much current would we have when the diode is in forward bias, when it's operating? And then when it's flipped, 0. But we still have the voltage across that guy. That's how we use our troubleshooting techniques to solve these circuits. If it's an open, it's going to measure everything, and there's no current flow. Okay, so this is just the generic run-of-the-mill diode. There's different types of diodes you guys will be using throughout the program. This is the schematic symbol for an LED. LEDs don't drop 0.7 volts. They drop a range. Red ones are about 2.2. Green ones are about 2.4. Blue ones are about 3.1. So depending on the color is going to be the voltage drop that it has. Most of the time we're going to be using red or green, so you can assume about 2.2 volts. Yeah, so multicolor LEDs work a little bit differently. They have some other electronics involved, and what happens on those guys, because like this one you'll have your LED, it'll look like this. It's got 4. I think the ones I have look something like that. Okay? What you'll see on the casing of these guys is you'll have a round spot over here, and then what you'll see on one side is the flat. The flat is connected to the shorter side until you cut them, or when you first get them, they look like this. But if you cut them, you have to go based on the flat. The flat is the negative. The flat is the negative. Okay? So with the 3-color ones, so this one just allows current to go one direction. This is your ground, and then you've got a red, blue, and green. And what these guys do is they don't necessarily take a voltage like the 2.2 or what we're taking. They take a range. So their full range is digitally 0 to 255. So if you were to break this up, you'd have 0 to 5 volts. And so then your voltage at this point is going to change based on that level. So you have 255 levels that your voltage can be at. And then whatever level it is, that's how bright it's going to turn on that individual color. So one thing, if you guys notice, if we look at colors, if you look on your computer, pull up Paint or anything, or even in the text, there's a little code down at the bottom that gives you like a 6 digits. Like FF, 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 or something like that with a pound sign in front of it. that is black. And so what it's saying, or white, I can't remember if it's white or black. But what you're going to see is it's basically full force of all the colors. So all the colors together is going to make white. Black is the absence of all the colors, or off. And so what you'll do is you'll put these voltages in. They behave differently because inside here, this has just the, like the P and the N material. This guy's got a little computer chip, and it's got a little surface mount resistors and things like that. So it interprets the signal and then spits out a voltage on top of that. But your diodes, the regular diodes, they're just the material that then glows when it passes a current through it. Tricolored LEDs are fun because you can get any color you want out of them. They're basically pixels. Okay? So your LED, it's going to have a range. So usually 2.2 to about 3.4, 3.5 volts. The tricolors, they're going to have a small current that they're pulling more off is what they're looking for, not a specific voltage. LEDs are used for what? Anything. Indications. Certain voltages. You know, you can have it designed. So like the circuit I built for my kids is we hooked it up. We built a potato battery and a lemon battery last night. And that was actually really fun. My oldest did not believe me that we'd be able to power a light with a potato. We found out that one potato gives you about 0.8 volts. You stick a zinc nail in one side and you shove a piece of copper in the other side, connect it together, you got about 0.8 volts per potato. You have to use multiple potatoes. We found this out too. So now we connected it together. We hooked 3 potatoes together and we were able to power this LED. Pretty good. It wasn't as bright as it could have been, but we were able to power it. That's what we did. We only had 3, so that's as far as we could go. Yeah. So the lemon we used gave us about 0.95 volts per lemon. So because it has more acidic acid in it. The potato has more of a phosphoric acid. And then the reaction between the two metals is what generates electricity. So they were way cooled out by this because we're powering lights by potatoes. What's cool too is where this kind of came from was World War I, World War II era. In cities that had been bombed out, there was no power. You had potatoes. You get potatoes everywhere. You could grow potatoes really easy. So they would string potatoes up in their house, put these metals together that you could get, because now you've got demolished buildings, you've got blown up artillery, you've got access to all these metals. You can now stick them into this potato, and they would use them to power lights inside their house so they could see at night. And it was something that was real quick and easy. If somebody was coming by, they could, you pull one of the nails out of the potato, and it shuts the lights off. And it's a renewable energy source. Huh? Huh? Dead serious. I'm dead serious. That's how these started. Take a lot of potatoes. A crap ton of potatoes. Serious? Yeah. You literally take a potato, you shove a zinc nail, and I just use a piece of copper. I had 12 gauge wire. And then you connect, that wire comes across to the LED. That's literally what we did. Okay. 3 potatoes, you'd have about 2 volts. Parallel potatoes, you'd get more current, but not voltage. So, but either way, the idea is, like I said, the LED is used as an indicator. The other circuit I built was I had the LED would first power on a green one, then the signal went through a capacitor and a resistor. because I wanted it to delay. What I was trying to do was get the capacitor to charge up slow. I got it to about 5 seconds. I put another LED across the capacitor. So when the green light turned on, you would count to 5, and then the red light would turn on. That was the other thing my kid thought was the coolest either, because now, like I was saying, Dad's stopping the flow of energy and controlling it to make it so the lights didn't turn on at the same time. That's an LED. They're very simple, but again, it's how you wire them up. The flat side is the negative. It's also the shortest leg. If they've been cut, obviously you don't have that reference anymore, but you still have the flat on the LED. Questions about the LED? You guys are going to use these things a ton. They're also one of the biggest drains on batteries. The next type of diode we have looks like this. Like that. This diode is called a Schottky diode. Now, a Schottky diode works the same as a regular diode with a couple of exceptions. It has a smaller voltage drop. So not much, but it goes down between 0.5 and 0.6. Now, on the diode, the 0.7 is an average, but we use 0.7. Schottky diode drops it down to about 5.5 for its average. It uses less power. Has a smaller current that's required to get it to drop this voltage. The biggest one has a faster switching speed. That's one of the biggest advantages of the Schottky diode, is the time it takes from a diode when you put a positive to negative current on, or make it forward bias, to switch it to a reverse bias and back. In between those switchings of the bias, you have a delay time. You have this switching speed. A Schottky diode is much faster than a regular diode at dissipating the energy and being able to reverse and go the other way, which is important for computers, calculators. You want those guys to be able to switch back and forth depending on how they're being used. Another option that they have is, because they have a faster switching speed, is a faster operating frequency. Higher frequencies means faster speeds, and this one can handle the faster speeds, so it can handle faster frequencies. Things are going to be changing a lot more at 1 gigahertz versus 1 megahertz. You got 1,000 times faster. Schottkys are where we get into, gigabit speeds, things like that. The problem that these have, so these guys are all positives. The big negative that we have, it has a lower reverse breakdown. So a lower reverse breakdown voltage is basically what happens, how much voltage you have to have this thing put in reverse bias to get it to conduct electricity. So it works faster, but it can't handle as high a voltage range. So for example, with a regular diode, we could put in a signal that had like an AC signal that was switching from plus and minus 20 volts. So it would come through with 20 volts, drop down to negative 20 volts. Regular diode can handle it. The Schottky diode, it has a breakdown voltage of, depending on the type it is, but for example, it only has 15 volts. So we can't run as much voltage through this thing. Because it's gonna start pushing it through when we want it off. It's gonna allow current to flow. which then is bad because usually we use them in like motors, and we don't want power going to the forward coils of motors when you're going in reverse. It'll stall your motor out and then burn it up. Schottky diodes you guys will get into and be using a lot more in 5th and 6th semester. Because that's when you start dealing with, and 4th semester, because you're dealing with high frequency operations. 1st, 2nd, and 3rd, you may use them a little bit, but they're there. Schottky diodes are starting to get more and more in electronics, in systems, mostly for the fact of their faster switching speeds. Everything we want, it needs to be faster. And right now, fast isn't fast enough. Okay, let's go ahead and go to break.